Diffraction describes the property of light whereby it bends as it goes through a narrow opening. So light will bend around corners and edges. This is a generic property of waves. If you have water waves that pass through a narrow opening, you'll see the water waves bend as they go through the opening. Because of this diffraction, you can actually get an interference pattern with only one single slit. So what ends up happening is that the waves from different parts of the slit interfere with each other and cause constructive and destructive interference. So the type of pattern you get with just one single slit is known as the Fraunhofer diffraction pattern. And it looks something like this. So if you shine light through a single slit, so you have a single wavelength of light going through just one slit, you will get a very bright central region that is wider than what you get with the double slit pattern. And that broad, bright central region is flanked on either side by a dark spot or a dark stripe, and then you have another bright region and then another dark, bright, dark, bright, dark, bright as you go outwards. And you'll notice that the bright spots get dimmer and dimmer as you move away from that central bright spot. So as we mentioned before, the reason why we get this pattern, this interference pattern, is that you have light coming from the different parts of the slit that can interfere with each other. So let's think about breaking the single slit up into two halves. So we're just doing this in our imaginations. There's no physical barrier there, but we just look at the light coming from the middles of the two halves of the slit. That light will have traveled a different distance from the two halves. If you choose a point other than the middle, then the light coming from this bottom half will have traveled a slightly further distance than the light coming from the top half. And so that difference in distance is going to be equal to this distance between where the middles of the two halves of the slit are. And so this distance here is a over 2. And then we multiply that by the sine of theta in order to find that difference in distance that the two rays travel. If that's equal to a half wavelength, then we get destructive interference. And then we can rearrange this expression to find the angle at which that occurs. So that's going to be where the sine of theta is equal to lambda over a, where a is the slit width. And then we can use the small angle approximation to substitute y over L for our sine of theta. So that's when we're just considering the two halves of the slit. But actually, you can divide the slit up into 4 parts, 6 parts, etc., and look at how the light from each of those parts of the slit is coming together and forming either constructive or destructive interference. So in actual fact, you get many dark spots, not just the one coming from the two halves of the slit. So overall, you can predict where the dark regions are going to occur using this expression here. So the sine of the angle to a dark region is going to always be equal to some whole number of lambda, the wavelength, divided by the slit widths. So m is going to be plus or minus 1, plus or minus 2, and so on. You'll notice that we don't have an m equals 0 because where m would be equal to 0, that would give us a 0 angle, and right in the middle we know there's actually a bright spot. So you have to have non-zero values of m, and that will tell you where all of the dark spots and where they are, where they occur. Now we don't actually have a formula for where the bright spots are. They tend to be basically just halfway between the dark spots. So if we use the small angle approximation, we can replace the sine of theta with y and L and get this expression for predicting where the dark spots occur as long as the small angle approximation is valid. So as long as we're not going too far away from the middle of the pattern, then the location of all of the dark spots is given by this expression where m is some non-zero integer. So this allows us to find all of those dark regions in the single slit pattern. So let's next look at this question. In a single slit diffraction experiment, as the width of the slit is made smaller, the width of the central maximum of the diffraction pattern, will it become smaller, larger, or will it remain the same?